Hi and welcome to a discussion with Noam Razin, where we talk about his paper Unintentional Unalignment, Likelihood Displacement in Direct Preference Optimization. The paper deals with the somehow counterintuitive phenomenon where you train a model to generate a certain kind of response, but in the end the likelihood of those responses actually decreases after training. We're going to discuss how this phenomenon arises and potential strategies you can take to try and circumvent that. I hope you enjoy it. So we will get to talking about direct preference optimization, which is kind of the core of the paper. But I think before that, it would be good if you could give an overview of just reinforcement learning from human feedback to begin with. I think that would be a good starting point to set the stage for the subsequent discussions.
Right. So I think the good place to start is that usually when you want to train a language model so that you can use it, for example, as a helpful assistant, such as ChatGPT, then the first stage is you pre-train the language model on a large amount of text. But then to actually make it useful, you need to do some fine-tuning or alignment, it's often called. So the most straightforward way to do so is supervised fine-tuning, which just means, okay, collect a set of examples. Okay, have a prompt and some response that you consider desirable, and then you fine-tune your model to produce these outputs. And this is usually the first stage in the alignment process that people do. The issue with it is that although it's very simple and appealing, obtaining high-quality responses is very expensive, especially for text generation. And so there's been a wide adoption of using methods that are based on preference data, which means that instead of getting high quality generation, you collect some candidate responses. Some of them can be good quality, some of them can be bad quality. For example, you can sample them for your model. And then all you need to do is to label which of these responses are better. And usually it's easier to get, for example, humans. Nowadays, people also use AI and other language models to do it, but you can more easily label which response is preferred as opposed to generating a very high quality response. Now, there are several ways to use these preference data, but in what you were referring to by reinforcement learning for alignment, this is kind of the first method, which was very popular, which people usually call reinforcement learning from human feedback, where the idea is that you have your preference data that you collected using human labelers. Occasionally, it's in the form of you have a prompt and two responses. One of them is labeled as the preferred response and the other as the dispreferred response. And the first stage that you do is you learn a reward model. Since you learn some neural network so that it gives high reward to the preferred response and a lower reward to the dispreferred response. So you fit your data that way. And once you learn your reward model, you can just use any reinforcement learning algorithm to train your language model so that it maximizes the reward. Usually you also add some constraints so that you don't stray too far from the model that you currently have. Because that can lead, for example, to the text that you generate to be kind of less coherent.
Hmm. Okay, if we're talking about the shortcomings of that approach, so I think one of the main ones is computational complexity of doing that. Could you perhaps elaborate a little bit more on why that approach is computationally expensive? Why is it very expensive to learn the reward model? Because I'm assuming that's the kind of bottleneck in this equation.
Right. So this method it can be very successful as kind of you can find evidence by the fact that companies, at least back when they reported what they were doing, they used it. ChatGPT was allegedly trained that way, and perhaps still state-of-the-art language models are trained in this way. But the reason that it's expensive is because first you need to train your reward model, which is usually also a very large language model. And then when you actually use reinforcement learning to train your language model, then you need to store your language model. You need to store your reward model because this requires a lot of memory. Usually, reinforcement learning algorithms actually have something that's called actor-critic frameworks, which means that in them you also need kind of a duplicate of your model. It's not just the language model, but you need another copy of it that is the critic. So first, this is
Mhm.
very expensive memory-wise. And also there's a lot of complexities going on behind the scene. Getting these type of reinforcement learning algorithms, formally they're known as policy gradient methods. PPO is perhaps the most common one that is used, but there are other variants that they have many hyperparameters and things that you need to tweak so that they work well. So
Mhm.
this creates kind of a very complex framework, which is both expensive in terms of memory and compute and can be quite unstable from time to time.
Mhm. Okay, so can we contrast that to direct preference optimization and elaborate a little bit more on like how exactly DPO improves upon those metrics, right? So I take it that these are the problems that we can potentially circumvent if we use DPO, but how exactly do we circumvent them?
Cool. So the main idea behind DPO and its other variants is that, okay, around, I think it's roughly a year ago from now, people noticed that, okay, you have this preference data. So you can do this multi-step thing of training a reward model and then using reinforcement learning. But okay, why not just use this preference data directly to train your language model? This is kind of the clean and nice idea behind DPO. Basically, you have your preference data, then you use some loss function over the preference data that teaches your model to generate more preferred responses compared to dispreferred responses. Usually these losses, they have this formula where they depend on the difference between the log probability of the preferred response and the log probability of the dispreferred response. And the idea is that to minimize the loss, you need to increase this gap, meaning you need to assign higher probability to preferred responses compared to dispreferred responses. And now notice that first off, you don't need reinforcement learning. Okay, it's just kind of a supervised learning framework. And it's also a single stage thing. Okay, you don't need to train a reward model and then do reinforcement learning. You just collect the preference data and fine tune on them. And this is very appealing because again, you're back to this more simpler setting and also less compute and memory intensive setting of supervised fine tuning.
Mhm. I'm trying to contrast that to what the equivalent would be if we would there be a way to use a reinforcement learning framework or similar, as in RLHF, where you wouldn't necessarily need to learn a reward model, or is that necessarily a requirement if you're taking a RL approach?
I think it's a bit of a definitional question of how do you define reinforcement learning? And
Hmm.
maybe this will vary depending on who you ask, but to me, reinforcement learning at its core is you have some reward function that you're trying to maximize. And I think you can either learn explicitly a reward model. Perhaps there's other way in which you don't explicitly learn it, but somehow you implicitly define a reward using your data. And I'm not too
Hmm.
familiar with any such methods. So I guess by the conventional way that people look at reinforcement learning to fine-tune language models, then yes, this requires usually training your reward model.
Hmm. Yeah, I'm kind of maybe going a bit off topic from the actual paper, but the reason for asking the question is it seems like in the RLHF approach, what we're doing is, as you said, we have a reward model and then we also have like usually an actor critic framework. And it seems like, so we are circumventing that more or less altogether by using DPO. And my question would be like, if there's a way to implement the alternate methodology in a more lean way, like you wouldn't necessarily need to implement an RL approach with an actor critic model. You could do that in by just having a reward function, for example, which seems like more of a one-to-one comparison to DPO. I don't know if there are successful approaches that do that and that are also more lean. And if there are approaches like that, what the main drawback is. I would guess if you're cutting out the actor critic part of an RL approach, that the main drawback you have is that you sacrifice a lot of accuracy for it. And then I guess you could make the argument coming back to DPO that you're also potentially sacrificing accuracy because you're just feeding preferences into a loss function directly without a secondary step. So it, all of this comes together, and my real question for you would be like, if you're comparing these two approaches, do we generally see inferior performance from DPO compared to something like RLHF? Because it seems like RLHF is a more powerful framework, or we're baking in more steps to try and make something that's reliable in the output.
Right. So I think the jury is still out about which method is works better typically. I think it a
Yeah.
lot depends on your specific setting on your data set. Right after DPO came out, I believe there were a few works that showed that if you tune and do RLHF correctly in some sense, then usually it leads to better performance. That's true. And there's been many kind of suggestions of why this might be the case. And for example, one of them is that RLHF is what you call an on policy algorithm in the sense that, okay, once you learn your reward, now you're sampling outputs from your model. The reward model gives you a signal of how good these responses are, and then you improve. And as you improve, you sample more responses which are better, and then you get a signal for them. And DPO, at least initially, how people did it is in an offline manner, which means, okay, you have your set of labeled the preferences, okay, there's some offline data set, it's called, then you simply fine tune over it. But I will say that this is not kind of a hard constraint on DPO. There's kind of two axes. There's the algorithm with which you use to optimize your language model, whether it's a reinforcement learning algorithm or this kind of direct preference learning algorithm, such as DPO, and how you obtain your data, which can be offline by take it from some existing data set or just produce once labels, then you consider whether they're preferred or dispreferred and use them, or you do it online and you keep sampling from your model, then you somehow label your new responses, whether it's through humans in the loop, which can be quite expensive, but you can also, for example, use a reward model in DPO, right? People in many cases do this. You can also train a reward model and then use DPO using the reward model. The benefit here, which is something that you alluded to, is there's multiple complexities and costs to reinforcement learning from human feedback. So one of them is learning the reward model, but since you're doing it once initially, may not be that problematic. And usually also the part of learning the reward model is also a rather simple part because it's supervised fine-tune. Okay, you have the preferred and dispreferred response. Essentially, DPO is kind of you directly train your language model as if it is a reward model. So this part is not too problematic. The part which can be costly and expensive in RLHF often is the fact where you do this reinforcement learning algorithm, for example, actor critic. And indeed, there are papers which show that, I think it's a paper from Anthropic, if I recall correctly, that if you use even kind of vanilla policy grain algorithms, and I think most popular one is reinforce, which is not an actor critic algorithm, which means it's a lot cheaper and has a lot less hyperparameters. It can also work quite good. So maybe in reinforcement learning settings, usually you need to do multiple tricks to get policy gradient to work well. But in language model settings, it's enough to do the simplest case. So you can indeed try to simplify more and make RLHF more efficient, but it's still, I think, hard to compete with kind of the appeal of just, okay, do you have a loss of your preference data and you just train the model over it.
Perfect. Thanks for the elaborate explanation. So with that, I think we can segue into actual likelihood displacement. Let me pull up the figure for that, and then in the meanwhile, if you wouldn't mind introducing just what that term means, and then we can talk conceptually first about it.
Yeah, so as I said, there's a very nice kind of appeal to doing direct preference learning, or DPO is the main method that kind of popularized it, but there are since then many methods. And the intuition behind them is that, as we already said, you should be increasing the probability of the preferred response and decreasing the probability of the dispreferred response. But people actually noticed in practice, because there are several papers about it, that when you train using these methods, often you see that both the probabilities of the preferred and the dispreferred response tend to decrease together. This is kind of what you see in the plot here. So the loss function, what it requires you to do is to increase the gap between them. Indeed, this happens. Okay, so the loss is minimized. There's no instability here. You can see that both here it's the log probabilities of the preferred response, which is y plus here, and the dispreferred response, which is y minus, they both decrease, but the gap between them increases. And this is a bit counterintuitive because if you look at the loss function and at the gradient, then there's a gradient that pushes upward the preferred response and downwards the dispreferred response. So it's not clear why it's happening. And also, because both of them decrease, this means that there's some other responses, here it's depicted by Z, which increase in probability. This is kind of what we refer to it by likelihood displacement, because you're displacing your likelihood. Instead of putting it on the preferred response, it goes to somewhere else, which you're not explicitly controlling. Okay, the loss function doesn't dictate exactly where your probability will go. And there are kind of two cases you can think of here. Okay, one, if these responses are similar in some sense or equally as preferable as your preferred response, then this is not problematic. Okay, this you can call it as a benign likelihood displacement. Perhaps to be concrete here, you can imagine a setting where you align your language model to refuse unsafe prompts. Okay, so if you give it examples where the preferred response is, I'm sorry, I cannot answer this prompt, or this preferred response, which is something that actually answers the prompt, and Z here, okay, the response that increases in probability is some other refusal. Okay, instead of saying I'm sorry, it says I apologize, I cannot answer this response. Then okay, this is not problematic. It's still okay. And the fact that DPO often works good means that in many cases this can be benign. However, in the face of it, it can also be what we call it catastrophic, right? The responses that increase in probability, since you're not controlling them, in some cases can be really undesirable. In the alignment setting, maybe instead of increasing the probability of a refusal response, you'll get suddenly a response which is harmful, and you're not really controlling for it explicitly. And although people have noticed that this likelihood displacement often occurs, there was no real good understanding of, first, why does this happen? And two, what are the implications of this? Meaning, when will it be benign, when it will be catastrophic, and in general, where does the probability mass go when it doesn't go to the preferred response?
Okay. Do you know if there's anyone who tried to tackle the problem of preventing the preferred response from actually declining in log probability? So, assuming you have a graph like this, one way of potentially addressing it, and this kind of is again another sidetrack that isn't necessarily, in line with the paper, but you see this, and the maybe obvious thing to do would be to try and prevent the gradient from y plus to ever be allowed to become negative in the training step. Is that something people have attempted? Do you know if there are methods to try and do that? And if they're not successful, if there's any idea why?
Right, so the previous works that noticed this problem, so a couple of them, or at least more than a couple, suggested that what you can do is you can add this regularization term, which is another kind of cross entropy level, so supervised fine-tuning term, people call it, on the preferred response. What this means is essentially you're making the gradient that pushes upwards, the preferred response, stronger. And
Mm-hmm.
indeed, what they showed is that this can mitigate this problem in many cases. In this paper, after we kind of characterize both theoretically and empirically when likelihood displacement occurs or when it is problematic, we take a slightly different approach. We actually look at the data. Because, okay, you can think of algorithmic changes to your loss function of how we can prevent this. But we show that actually if you filter your data or curate it, kind of collect data in a smarter way, then you can also prevent this and often go beyond what you can do with just adding regularization. Okay, so adding regularization can help you mitigate this in some or many cases, but if you collect your data in a better way, this can go beyond these type of methods, at least for the settings that we consider.
Mm-hmm. Very good. So we'll get to that in a second. Before that, let's have a look at the example. So I think in section 3, you have this table, this one. And this one will be interesting to talk about a bit more, I think, because this highlights the benign and the catastrophic scenarios. Would you mind going through like what this table is meant to represent?
Yeah, so the result that we see here to me was very surprising. And the idea here is that past work, they kind of attributed likelihood displacement to different complexities that you can have in the pipeline. For example, maybe your model capacity is limited. Maybe it simply cannot increase the probability of the preferred and decrease the probability of the dispreferred because it has a limited capacity. Or maybe it's because you have a large data set and it's unable to fit it all. Or another work suggested that you have responses which have overlapping tokens, and this can lead to the problem. And we wanted to ask, okay, what is the simplest setting in which this can occur? Kind of to find the core reasons why likelihood
Mhm.
displacement occurs. So we did the simplest thing that you can imagine, which is you take a single prompt. Here the prompt is from what is known as the persona dataset. It's basically a dataset where each prompt is a statement, and the model needs to respond with a single token. Okay, the responses here are just a single token each, whether it agrees or disagrees with the prompt. Okay, for example, the preferred and dispreferred responses here, which is what you see by y plus and y minus, these are just kind of synonyms of yes and no. And so we train using DPO, different open source models of different sizes, on a single prompt using different pairs of preferred and dispreferred examples. And the first thing that this table shows is that the probability of the preferred response almost always decreases. Okay, here in all of these cases, it decreased and by substantial amount, which means that even in this simple case, likelihood displacement is prevalent. Okay, we can see that decreases are quite large.
Mhm.
Now, when you take tokens which are similar, opposite in meaning, for example, yes versus no, we found that usually likelihood displacement is benign. So we can see that the tokens that increase most in probability, this is on the right, then this is kind of variance of, yes, different capitalizations, white spaces, things that we consider to not be too problematic. However, if you take two tokens which are similar in meaning, for example, you want them all to say no instead of never, then it turns out that actually it can increase the probability of opposite tokens. So suddenly yes shoots up in probability. And it's a very large increase. In some cases, the probability for yes goes from near 0 to 0.6. And to here, we refer to this as catastrophic. Obviously, this is a controlled thing that is meant to illustrate things, but you could imagine that you have some language model, and currently it produces text in some style. For example, it says, never, I would not do that, but you would not to tweak it a bit. You want to say, don't say never, say no. And to me, it was very surprising. I wouldn't expect that, okay, you train them all to say no instead of never, and it starts saying yes.
Mhm. Yes. In terms of the potential outputs that you had, like if we're considering the potential outputs that you had from the model when you ran this, you said that there were single token outputs that the model was meant to respond with. How large of a set of possible tokens did you have in the output space? Because I
So
guess that's
this,
also a relevant feature of this, right? Like if you have a very small space of possible outputs, I guess likelihood displacement, well, it's hard to say exactly what it would do to the likelihood displacement, but assuming you only had two outputs at least, then I don't see how you would have a likelihood displacement if you're doing this and simply increasing the probability of one versus the other, and there's no third response that the model or that the system could give, then I guess their relative probabilities would still be intact or still get updated in the correct direction.
right, so this is a very good observation. Indeed, if you have only two tokens, then likelihood displacement cannot occur. You can only increase the preferred response and decrease the dispreferred one. Here, we don't restrict the possible tokens. So we're choosing a preferred token and a dispreferred token, but you still have the original tokens of the model. So it depends on which model, but usually you can have between a few tens of thousands to some of these models nowadays have more than 100,000 tokens in their vocabulary. And on the right, what we're showing is the tokens that increase most in probability instead. So indeed, when you do DPO on this single preference sample, then out of all possible tokens, okay, we're not restricting these tokens. In many cases, you see that yes, or variants of yes, increase a lot in probability when you train them out to prefer no over never.
Mm-hmm. Okay. Good. So that brings us to the part on theoretical investigations. So let's talk about the two main observations I think would be a good starting point here for why we see this now. So we've given sort of an account for what it is that we see, and it would be interesting to get some more information on why it happens. So would you mind introducing first of all takeaway one here, and then we can talk about the details surrounding that.
Yeah, sure. So the theory, what we end up doing is, okay, we want to understand how the log probabilities of the model behave. Okay, because we want to know when will the preferred response decrease in probability and which other responses will increase. What we do is we track how these log probabilities evolve during training using gradient-based methods, which is how people train to minimize these type of loss functions. And we characterize two uh, different kind of factors here which contribute to likelihood displacement. And they are both relating to the embedding geometry of the model. Basically, the embedding geometry dictates the probability that the model produces and how they evolve. So the first one, takeaway one here, regards to the embeddings, or more correctly, the unembeddings of the tokens. So just to introduce what this means, okay, how does a typical language model looks like? You have some neural network, usually it's a transformer. You give it a sequence of tokens. Here it's the prompt, and here it's a single token, so it's the preferred or dispreferred token. And it gives you a hidden embedding, which is called H. And then to produce the probability for your outputs, you multiply this hidden embedding by some matrix W. This is often called a token unembedding matrix. The reason is because each row in this matrix W, you can think of as an embedding or unembedding, people often call it, of that token. And it turns out that when the unembeddings of the preferred and dispreferred token, look here you can think this is intuition for the single token case, the experience that we just talked about. When they're similar in the sense that their inner product is higher, Okay, this is the kind of point one in this takeaway. Then you will have more likelihood displacement. This formalizes in one way the intuition that people, I think, had before our paper, even that in a sense, when the preferred and dispreferred responses are similar, it will be more problematic. But it was not clear in what sense do you mean when you say similar. For example, people suggest maybe it's just similar tokens in the sense of you have an overlap between the tokens in your responses. And here we formalize this in the sense of the inner product between the token and embeddings. And the second part is, okay, which tokens will increase most in probability? Then it's the tokens whose unembedding aligns with the direction of the preferred token minus the dispreferred token. Okay, this WY plus minus WY minus. And why this can lead to kind of catastrophic likely displacement is because WY minus, often in practice, if you just check the unembeddings of standard language models, can contain directions which are orthogonal WY plus, and they can often be very large. Okay, the direction orthogonal to WY plus, which is the direction that dictates the preferred token, is often larger when you look at this difference. Okay, this WY plus minus WY minus, usually it will have a larger component that is orthogonal to WY plus. And it is well known that often these unembeddings, they capture semantics or meanings of words. So it means that the tokens that can increase in probability can often be unrelated or opposite in meaning to the preferred token. So this gives an explanation for what we saw in the single token experiments.
Could you reiterate why the difference between these? So specifically WY plus minus WY minus here. You said we expect that to have an orthogonal component, which is larger than the original case. Could you again elaborate on why we expect that to be the case?
All right, so I'm not sure we expect that, but just a matter of fact that if you look at language models, you take your favorite open source pre-trained language model and you look at these unembeddings, for example, for the token pairs that we use or just standard token pairs, then this is in many cases what happens. So our analysis, it doesn't really make any assumption about these embeddings because we really can't control them. Depends a lot on your pre-training. It's very complex. So what we do is can just measure empirically how these quantities look like. And then you can see that indeed they will have a larger orthogonal direction. And this is why this occurs.
Okay. And if we think again about how direct preference optimization works, so we have these two components, y plus, y minus, and we're trying to change their relative likelihoods. How exactly do we do that from the perspective of equations in our loss function? Do we try to suppress one of them actively, wy minus in that case, or sorry, just y minus in that case, and we don't so much affect y plus, but it's sort of a secondary consequence that it also gets reduced in many of the situations, or do we do something else? I'm just trying to wrap my head around the first part here. So we're saying that the inner product between these two embeddings being similar can cause likelihood displacement. What that kind of tells me, or at least what it sounds like to me, is that if we're trying to suppress y minus and wy plus and wy minus are similar in terms of inner product, then you're likely to suppress that part of the matrix also for the y plus case. And that's potentially not necessarily why you would see a large likelihood displacement for other values, but at least see a large decrease in likelihood for the y plus response as well, if that makes sense.
Yeah. So I think it might be useful to go to the loss equation. It's in section 2, just to be clear about how the loss exactly looks like in these cases. And this relates to the initial part of your question. Yeah, here. So these type of losses, how they look like, you have some little L here, which is varies between the different variants of DPO that you use. Doesn't really matter for our purposes, but it depends on the gap between the log probability of the preferred response and the dispreferred response. So what the loss tells you to do, to minimize it, you need to increase this gap. So it doesn't tell you how to increase this gap. This is why likelihood displacement can occur, because you can also increase it when they both decrease. They need to increase the gap. And this is also why this WY plus minus WY minus term appears, by the way. You can see that there's this contrastive term here where you contrast the two log probabilities. And regarding maybe the second part of the question, so when the inner products of the token and embeddings are similar, what this means, in other words, is that if you look at the gradient that pushes downwards, the dispreferred response, then it will be aligned also with the gradient that pushes upwards the preferred response. So it can negate it and also push the preferred response downwards as a consequence. This is another way, perhaps, to look at it.
Mhm. Is there some heuristic understanding we have between the loss function here and the token unembedding matrices themselves? Like, is there anything we can say about if you want to increase like the probability of an outcome, what effect that likely has on the matrix?
So we can compute the gradient for the log probability of some response and see what direction it dictates over the token unembedding matrix to increase that log probability. And indeed, this is what our analysis basically does. We look at the gradient of the preferred response, the gradient of the dispreferred response, and then this essentially dictates how your log probabilities will evolve. And the interesting part is due to their interaction. Okay, if you only have the log probability of the preferred response and you only try to maximize that, this is essentially supervised fine-tuning. And in these cases, the preferred response will only increase in probability. Okay? But
Mhm.
because you have this also negative direction, we try to push downwards the dispreferred response, this can apparently lead to these interesting and weird behaviors that you might not initially expect.
Mhm. Okay, very good. So with that, let's move over to the second one as well and talk a little bit about that. So we have this one. If you wouldn't mind explaining takeaway two.
Right. So until now, we discussed this more controlled setting. We had a single output token, and I think this was very useful to pinpoint exactly why likelihood displacement can occur, what is the simplest setting which can happen. But now we want to go to more realistic settings, and there the responses, they have multiple tokens. And when you have multiple tokens, now it's not only the token and embeddings which matter, there's also a relation on the hidden embeddings. So just to remind what these are, okay, this you have your network, you give it a sequence of tokens, and it produces the hidden embedding. This is kind of the final output of the network before you multiply it by the unembedding matrix W that we previously talked about to get your logits from which you get the probabilities. Okay?
Mhm.
And in this multiple token case, what our analysis suggests is that likelihood displacement occurs due to a similarity between these hidden embeddings. Now, it's not just any type of similarity. It's not just you take the inner product between the last hidden embeddings, which is maybe a natural thing to do, but rather a more correct in some sense. Similarity measure is what we call here the centered hidden embedding similarity score, kind of the chess score, which is you take the inner product, okay, maybe to parse what is going on here. So for each response, for example, y plus, you have multiple hidden embeddings. You have one for each prefix of the response, right? Because to generate the probability, it is done autoregressively. So first, you model, you give it your prompt and your first token of the response, and it gives you h of x, comma, y plus, and only the first token of it. This is one
Mhm.
hidden embedding. And then you also input the second token of the response. This gives you another hidden embedding, and so on. So each response essentially has a number of hidden embeddings that is equal to the length of the response. And the similarity measure is you take an inner product between the sum of these hidden embeddings for the preferred response and the dispreferred response, and you also center it by the square norm for the centering for the preferred response. So in other words, maybe to simplify it, this is some measure that tells you how similar, in some sense, the hidden embeddings of the preferred and dispreferred response are. And it formalizes the intuition for now the more realistic setting that when your responses are similar, in this sense, likelihood displacement will occur more often.
Okay, that makes perfect sense. Were you in any way surprised by the fact, or maybe let me ask it like this first. How did you actually arrive at the chess metric? So was this something that you thought was natural as just a stipulation of what a good metric might be, or was there some other approach at actually arriving at this?
So the intuition that we initially had is that must depend on the hidden embeddings and the token embeddings. So this is kind of the only place where the dependence where that determines how likely displacement will occur and what will happen. But it was not clear how this dependence looks like. Our analysis, it derived equations that govern how the log probabilities evolved, and this chess score pops up from there. Because we have a term there which is slightly more complex with this, depends on some other terms, but based on it, we derive this chess score. We simplify what our theory says by looking empirically at how different terms in the equation that we have behave, and this allows us to roughly set them to something which is more interpretable, and from this, the chess score pops up. So it's not something that we expected initially, so we knew there's got to be some dependence on the hidden embeddings, but this exact form popped out from the analysis.
Okay. Would there be any way to safeguard or to more or less guarantee that this is the best metric that you can get? I'm just thinking of ways to like if there's some derivable result to tell you how much inferential capability you would get from this, because this seems to be a good metric, and also on the figures that we'll look at in a second, it also has better capabilities of inferring, at least seemingly, whether we will have likelihood displacement compared to some of the others that were previously assessed. With that being said, is there an upper limit that we somehow could estimate for how good the best theoretical possible metric would be for estimating this? Do you have any ideas there?
Yeah, so it's a very complex question. It's also a good one. And in no way do we have a formal proof that this is the best measure in some sense that you can use. Our analysis, it looks locally at the current time step, how things behave. And perhaps to better understand what completely characterizes likelihood displacement, obviously we leave some questions on the table. It's not that we close completely the whole story and we have a perfect understanding of it. Then you need to analyze the full trajectory of training and how things behave along that. And maybe that can lead to even better measures. It's a lot more complex to analyze and it's out of the scope of what we did. But the reason that I think that this is a good measure, as you said, later on when you take it and examine empirically how well does it allow you to identify when you will have likely displacement, it works very well. So in no way do we know if this is the best measure in some sense that we can use, but it has been useful for our purposes, and I think that it does have a lot of potential.
Mm-hmm. Maybe we can look at the figures associated with that comparison as well. I think we have it here. So this one would be quite interesting if you could just introduce, I mean, the chess score, that one we talked about now, but what these other benchmarks are and what you're illustrating with the figure.
Okay, so the idea is, okay, our theory pointed to this measure, and now the next natural thing to do is look, let's evaluate it in practice. Let's see if it indeed correlates with what happens in practice. And the idea is that you take some standard data set. Here it's ultra feedback. This is a data set which contains prompts and preferences, preferred response and dispreferred response. And we want to see whether we can use our measure to identify which samples are problematic in the sense that they cause likely displacement. So you can compute the chess score for all the samples in the training set and partition them into subsets that have different similarities. This is what the x-axis in these plots is. So I have here 5 different subsets. On the left, this is the subset which has the most dissimilar preferences, and on the right, it's the most similar ones. So we did this for the chess score, and we also wanted to compare it to a couple of natural baselines. So the first one is the edit distance similarity. This means that you have your 2 responses. The edit distance is essentially the number of edits you need to do to one response so that you transform it into the other response. So if you're, for example, you have 2 responses which are exactly the same but differ only by a single token, then you have an edit distance of 1. Now, previous papers, some of them suggested that responses with a small edit distance, they cause likely displacement. This is why we compare to. And the third measure here, which we call hidden embedding similarity, this is more of a sanity check or a more natural candidate. Is okay, we propose this chess score, which has this form of it depends on the hidden embeddings in a way which is more complex than just taking the inner products of the last hidden embedding, which is maybe something that is natural to do. So we want to verify, is it indeed better? Okay, maybe all we need to do is you take your response, you compute the final hidden embedding of the network, okay, for the preferred response, do the same for the dispreferred response, and just take that inner product. A lot simpler. Also depends on the hidden embedding, but a lot simpler. So maybe this is all you need to do. You don't need to compute the chess score. And what this plot shows is that, okay, the y-axis, this is how the preferred response changes along probability as you train using DPO So here we have two models. On the left, it's the Gemma 2B model. On the right, it's the Llama 3 8B model. And what you can see is that for the chess score, it correctly ranks the samples in terms of how they cause likelihood displacement. You see on the left, as we expect, there's no likelihood displacement. The preferred response only increases in probability, and this is expected because these are the responses, the samples for which the responses are the least similar. But as you go towards the right, you see that you have more and more likelihood displacement. Specifically, the area in red, once this change drops below zero, this means you have likelihood displacement, and you see in the two subsets to the right, then you have a significant drop. On the other hand, you see that the other measures, they don't really correlate. They're not really indicative of whether or not you'll have likelihood displacement, meaning you take samples which are similar or dissimilar or with medium similarity, and it roughly gives you the same result. Meaning they're not really able to identify which samples are problematic.
Are there any additional scores or metrics in addition to these that were raised in previous papers as potential candidates?
As far as I know, not really. I think in previous papers, the only one that was brought up formally was the edit distance, and we also compared to the hidden embedding similarity just as a sanity check.
Okay. Okay, cool. Is there anything else you think is worth highlighting just on this figure before we move on to the next section?
No, I think the bottom line to take from this figure is just that the chess score that we introduced, indeed in practice, allows us to identify which samples contribute most in a dataset to likelihood displacement. And perhaps what we'll talk about next is that you can use this to try and mitigate likelihood displacement and some of its harmful implications.
Yes. So let's have a look at the next figure and then we can dive into that. So would you mind introducing the topic that you just gave a sneak peek of, and then we can start discussing this?
Yeah. So to demonstrate where this measure can be useful, we examined one more realistic use case of doing preference learning. Okay, so before we talked about these simple single token experiments, more controlled, and let us examine where you can find likelihood displacement and why it happens. But now I want to see, okay, does likelihood displacement have harmful consequences in more real world settings? Okay, something that are beyond these kind of toy controlled settings. So what we do is we consider the setting of trying to train your language model to refuse unsafe responses. This is the example that I brought up initially. The idea is you take a set of unsafe responses from some benchmark, and you do the standard or vanilla direct preference learning setup, which is for each response, you sample for each prompt, you sample two responses. Then you label them using either humans or some judge model. Here in this specific experiment, we use a judge model from a benchmark that people proposed, which can tell you whether this response is harmful or not, in the sense of did the model refuse to answer this unsafe prompt, or did it answer it, and so this is a harmful response. And so you label the refusals as preferred compared to dispreferred responses. And if you have responses which are of the same type, then you can tie break using also a reward model randomly, however you prefer. And now you can train using DPO your language model to produce refusals more often. And the interesting part here is that when you do this, actually you get likelihood displacement, which is catastrophic. Okay, the probability of the preferred responses of the refusal decreases, and instead it goes to harmful responses. What you see in the bar plot here on the left, this is the left two columns. So we take two moderately aligned language models. This is Gemma 2B instruct and also Llama 3 8B instruct. These are models which are also underwent safety alignment phase. This is a model by Google, a model by Meta. And this is what initially, this is the gray bar, you see that they refuse roughly 75 to 80% of the unsafe prompts. But when you try to make them refuse more prompts using this method, then likely displacement causes the refusal rate to drop. Okay, so you do DPO, and this is what is really surprising here, at least to me, that the only purpose of this training pipeline is to increase the refusal rate. Okay, you're trying to make the model refuse unsafe prompts. This is the only thing that you're training it for. And instead what happens is that it starts answering these unsafe prompts. So
Yes.
I think that was like quite cool. Like to me, it was very nice to see that actually in real world settings, you can see these very surprising likely displacement behavior.
Do you think that's very dependent on which data set you use, or would you expect similar results if, like, yeah, on different data sets as well? Do you think it's
Right.
agnostic?
So you're spoiling the, okay, it's not a surprising one, but the data matters here a lot. And this is one of the main conclusions that we make. And maybe to give a bit more detail, okay, so why does this happen? Why do we have this catastrophic likelihood displacement? So it turns out that since your models are already markedly aligned, in many cases, over 70% of the cases actually, they'll generate two refusals. So your data set will often have, you have an unsafe prompt, and you have a preferred response, which is a refusal response, and a dispreferred response, which is also a refusal. And this is kind of analogous to what we saw before in the controlled experience, where you train the model to do no, to prefer no over never, and it output yes.
Mhm.
And here you get an analogous phenomenon where you train it on a data set which has a lot of samples for which you have two refusals, and this leads to likelihood displacement that transfers probability mass from a refusal response to harmful responses. So this is analogous to what we saw before. And the data matters a lot, as you can understand from this, specifically, which is what we show in the, essentially you have here in the bar plot on the left. Okay, so the two right bar plots is two variants where we modify the data on which we train on. So one of them is you can think if you're trying to get gold data. What it means is instead of sampling responses from your model, you get high quality responses by, for example, you sample from a variety of different models. Some of them are aligned, some of them are not. Then you get a vast difference between the responses. Some of them are refusals, some of them are not, and then you label them using humans. And if you use such a data set, then you don't have this problem. Okay, so you don't have likelihood displacement, and also the refusal rate increases and doesn't drop. And interestingly enough, instead of doing this more expensive data curation, for this setting, we show that you can use the chess score. This is the DPO filtered bar on the right to filter out responses, samples from the original data set. So what we do is you take our data set, the one that we generated by sampling from the model, for which if you just train on the full data set, you get this large drop. And we only took the bottom samples, those which have the least similar responses according to this chess score. And you can see that this leads to a huge increase in the refusal rate. Basically, now you don't have this problem of catastrophic likelihood displacement.
Mhm.
So the
In terms
data
of
matters a lot.
Mhm. In terms of the utility of a filter data set like that, do you think you could still train it, roughly speaking, in the same way? So, like, let's say you have a particular response that you want to decrease the likelihood for, and then you want to find in this filter data set something else that would be your preferred response. Because I take it that that's kind of the approach that you would take. You would have, like, identify a response that you want to use as your this preferred one, let's say, and then you do a filtering as a next step to that, and then from that filter data set, you would then select your preferred response. Am I thinking about that from a like step by step or like pipelining perspective in the right way to begin with?
So this is a very interesting approach, and I think there's a lot of follow-up direction that we can do. In this paper, we took just a more kind of approach of you take your full data set, you see what happens on it. Here you have the refusal rate drop and the log probability of the responses on average decreases, and we mitigate this. But I do think that it can be an interesting direction to try and do something which is more fine grained, which, if I understand what you suggest, for example, you find one prompt or one or few prompts and responses for which you have likely displacement, and you want to understand which samples in your data caused it. And then you can try to remove them to mitigate the problem just for this response. I think these are all interesting directions, but it's not something that we did in this work.
Okay, help me understand then again how you filter DPO filtered. So it seems to me now, based on your answer, that you filter it actually before you select any responses, either positive or negative, or preferred slash dispreferred.
So it's after you get your responses, you sample, you have your data set. Okay,
Mhm.
here it's you sampled responses from your model and you labeled them as preferred and dispreferred. And at this stage, before you train your language model using DPO, you can compute the chess score for each training sample. Okay, the chess score is the formula that we saw before, depends on the hidden embeddings of your language model, compute it. And then you can rank the samples according to the chess score And let's say you take just the bottom 5 of 10% of the samples. Of course, it's a question for each data set, how much should you filter and when? And I think this is something that really depends on the setting that you are. But here, you can filter a lot of the data. For example, in these plots, we only kept 5% of the bottom of the most dissimilar responses. This is actually what you see on the right plot, by the way. The right plot, it shows you the ranking according to our chess score for the different types of responses. So in green, these are prompts which have one refusal response and one non-refusal. These are kind of the good responses where the two responses differ both intuitively and also according to the chess score. On
Mm-hmm.
the right, on red, this is two refusal responses. You see, this is the vast majority of samples, over 70%. In the middle, you also have some samples which have two non-refusals. And by the way, it's important to say that you might think, okay, maybe these are the ones which are problematic. And indeed, they can also be problematic, okay, because you have samples for which the preferred response is a non-refusal. But also, if you remove them from the data and just train on the two refusals, you also get the same behavior. Okay, so it's not that they are the ones that are causing these issues. And the plot on the right shows that the chess score, it correctly ranks the samples in the sense that it marks the samples which are most problematic in the sense of causing likelihood displacement as those for which intuitively the two responses are the same type. They're either non-refusals or refusals. So if you filter out and keep only the bottom ones, you're kept with more high quality data in a sense that you only have a preferred refusal response and the dispreferred is a non-refusal.
Mm-hmm. Would there be a way to to allow two refusals, for example, into the training model without significantly affecting the performance? Because if you have two refusals, likely they would be quite similar in general on the chess score. That's my takeaway. And if you there might be some refusals that are less similar to each other, but did you do any investigations to try to allow two refusals, for example, if you just filter out that subset of input slash or of data, um, and then do a filtering on those? Like, does that significantly affect the performance?
Yes, so for this setting, what we tried, so we tried a few percentage of data that we keep. So the gray line that you see on the plot on the right, this is the 5% of the sample that includes pretty much almost only samples which have one of each and a few
Yep.
samples from the two refusals. And we also tried higher percentages, 10%, 15, 20, and until 15%, which I think includes roughly half and half in terms of one of each and two refusals, it still works in the sense that you mitigate this refusal rate drop. But after that, we find that it starts doing problems. You start getting this similar drops in performance in terms of refusal rates here.
Mhm. Because then it seems like if you would construct a study for, like, let's say you would put this into use in an application setting, really what the results here tell us is that you want to construct your data such that you have one of each. No, like in the data generation step, when you create your samples for training your model, it seems like the critical takeaway here is if you want to minimize the likelihood displacement that you get, the best approach to do that is to make sure that you have one refusal and one non-refusal in the data.
So in this setting, where you train the language model to refuse unsafe prompts, then yes, this is what this suggests, and maybe this is what you intuitively would expected beforehand, but it shows the problems that you might not expect from having two refusals and how you can also filter automatically. I think the interesting part here is, okay, this showcases the potential of using the chess score for filtering data. And here
Mm.
you can actually categorize, okay, one of each is good, two non-refusals is problematic, also two refusals, but in general settings, instruction following settings, where you have a prompt and two responses which just follow the response, then you don't have this clear categorization and also not clear of which responses are similar or not. Right here, another way you could filter is just you look at the labels, you look which are refusals and which are not, and just okay, just train on the one of each. But in real world settings, you don't have such a category. You don't know which samples are problematic or not. And this is where I think that the chess score can be potentially useful, where you can use it
Mm.
to filter data which causes likelihood displacement even when you don't have any other way to automatically identify which samples might be problematic.
Hmm. Okay, cool. Very good. We're starting to, yeah, run out of time. So I would like to summarize the paper and sort of next steps that you perhaps would take. I don't know if you're planning to conduct more research in the same area, and if so, if there are like key points that you think are not just relevant for future research, but really relevant to the point where you think it mandates, yeah, future attention.
Yeah, so this point we discussed it in there's a part at the end of the paper that maybe you can show it. It's the limitations
Yeah,
in
sure.
future work.
Hmm.
And I think there's a few directions which are interesting to follow up here. So the first one in terms of the theory. So we characterize some part of why likely displacement happens, but our theory also has limitations. And I think there's also an interesting work to be done in improving it. But perhaps more importantly, also from a practical perspective, is that one, we showed a case where likely displacement is catastrophic and it can lead to these unexpected unintentional unalignment phenomenon. And because DPO and these type of methods are increasingly used, although in many cases they are successful, I think it's very important to try and understand better where you can get these kind of catastrophic phenomena. We can understand where can they fail so that we can
Hmm.
improve and overcome these failures. And specifically, the chess score, we showed that it had potential in the specific unalignment setting, but more broadly, I think there's still work to be done to explore whether it can be useful for data filtering in general settings, instruction following settings. Maybe you can filter some data in just standard data sets. This can help you improve performance on instruction following because it will help mitigate some of the perhaps harmful likely displacement. And also we can think of more complex pipelines, okay, not just data filtering, but when you collect your data, okay, then often you can try and get responses from multiple sources, not just generate from your own model, generate from multiple models that have different capabilities. Then you have a pool of responses, and maybe using chess score, you can choose which responses you take as your preferred and dispreferred response so that they're not as similar. Okay, you take
Hmm.
responses that have a lower chess score. So I think there's a lot of interesting work to be done in terms of verifying how useful it can be in more general settings beyond the one that we consider in this paper.
Okay, very good. So I think with that, we can wrap it up. I appreciate you taking the time, really. So yeah, thanks, Noam, for doing that, and have a good rest of the day.
Yeah, thank you for having me. It was a lot of fun.